What are the minor losses, minor energy losses, or minor head losses? We have already discussed the major energy loss or the major head loss, that is due to friction. But other than this, other than the friction loss, we have some minor energy losses. So that is due to these following reasons. That occurs mainly due to the sudden change in velocity of the fluid flow. So these losses are loss of head due to sudden enlargement, loss of head due to sudden contraction, loss of head at entrance of pipe, loss of head at exit of pipe, loss of head due to obstruction in pipe, loss of head due to bend in the pipe, loss of head due to various pipe fittings. So let us see each one in detail. First one is loss of head due to sudden enlargement. You can see the pipe here. Because of the sudden change in the cross section of the pipe, the fluid flow cannot trace the the change in the path. Because of this, there are some eddy formation here. The fluid flow will occur like this, and there is some eddy formation here which causes the loss in head. Now, how to calculate the loss in head? At section 1 we have the pressure force, and at section 2 we have the pressure force here P2A2, and at section 1 we have the velocity V1, and at section 2 we have the velocity V2. And in this section we have a pressure that is equal to P dash, which was experimentally found to be equal to P1. If you apply Bernoulli's equation between section 1 and 2, you will get P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus head loss. Since they are at the same level, you can cancel off Z1 and Z2, and you can write P1 by rho g plus V1 square by 2g is equal to P2 by rho g plus V2 square by 2g plus head loss. And head loss can be written as P1 by rho g minus P2 by rho g plus V1 square by 2g minus V2 square by 2g. And if you write the total force in the x direction, this is equal to, assuming we don't have the friction, there is no friction because it's a short pipe, so the value of friction loss can be neglected. So the total force acting will be equal to P1A1 plus P dash A2 minus V1. P dash is the pressure in this section, the area where the eddies are formed. P dash into A2 minus A1 minus P2 A2. So this is the force here. This is the total force acting. So if you substitute for P dash, that is equal to P1, you will get P1A1 that is equal to P1A1 plus P1 A2 minus A1 minus P2 A2. So let us continue with this equation. So Fx is equal to P1, it is A1, P1 A1 minus P2 A2. If we simplify this, we will get P1 minus P2 A2 is equal to P1 minus P2 into A2. According to Newton's second law of motion, this Fx, net force, is equal to mass into acceleration, P1 minus P2 into A2. This acceleration is equal to m into acceleration is equal to rate of change of momentum in the x direction. This rate of change of momentum can be written as m dash into v2 minus m dash into v1. This is the rate of change of momentum. And this m dash is actually equal to rho a2 v2 into v2 minus m dash can be written as rho a1 v1 into v1. Both rho 2 a2 v2 is equal to rho a1 v1. This is the one-dimensional continuity equation. So you can write it like this. So this will become rho a2 v2 square minus rho a1 v1 square. And if you rearrange this equation, that is rho 2 a2 v2 square minus this a1 can be written as, we have already seen, because this is a continuity equation, a1 v1 is equal to a2 v2. So a1 can be written as a2 v2 by v1 into v1 square. So this will become rho a2 v2 square minus rho a2 v2 into v1. So if we equate, we have already got what is fx. Fx is p1 minus p2 into a2. This is equal to rho a2 v2 square minus rho a2 v2 into v1. So p1 minus p2 is equal to rho v2 square minus rho v2 v1. So p1 minus p2 by rho g is equal to v2 square minus v2 v1 by g. So earlier we have seen the head loss is can be written by a modified Bernoulli's equation. This is equal to p1 by rho g minus p2 by rho g plus v1 square by 2g minus v2 square by 2g. If you substitute for p1 minus p2 by rho g, here you will get v2 square minus v2 v1 by g plus v1 square by 2g minus v2 square by 2g. And this head loss is equal to 2 into v2 square minus v2 into v1 by 2g plus v1 square by 2g minus v2 square by 2g. And this head loss is equal to v1 square minus 2v2 v1 plus v2 square by 2g. If you simplify this, and this is equal to v1 minus v2 the whole square by 2g. So this is the head loss due to the sudden enlargement in the pipe. This is the formula for calculating the head loss, v1 minus v2 the whole square by 2g. Now what is the loss of head due to sudden contraction in the pipe? You can see the figure. This is a pipe which has got a sudden contraction. Here you can see that fluid flows here. It will converge together at a portion here. This is called vena contracta, and after that it will enlarge. It will diverge. The loss occurs because of this sudden diverging, because of this sudden enlargement here. Because up to vena contracta it will flow smoothly. So this is actually the case of sudden enlargement. It will converge smoothly up to vena contracta. After that it will diverge immediately, which causes the loss. So this is also another case of sudden enlargement in pipe. So because of the sudden enlargement, you have already seen what is the equation. That is head loss is equal to Vc minus V2 the whole square by 2g. This is the head loss due to the sudden enlargement in pipe. So sudden enlargement occurs from this vena contracta region, that is C, to the region 2. So it can be written as Vc minus V2 the whole square by 2g. But you don't know the velocity at Vc to calculate the head loss. So this can be written as V2 square. If taken outside, you can write it as V2 square into Vc by V2 minus 1 the whole square by 2g. And you know the coefficient of contraction is equal to the area at vena contracta by area of this orifice, or you can write it as A2. If you substitute here, you will get V2 square into A2 by AC minus 1 the whole square by 2G. This is equal to V2 square into 1 by coefficient of contraction minus 1 the whole square by 2G. If the coefficient of contraction is usually 0.62, if you substitute that, you will get head loss is equal to 0.375 V2 square by 2G. In case a coefficient of contraction is not given, we can approximate this value as 0.5 V2 square by 2G. So this is the head loss due to the sudden contraction. Now loss of head, what is the loss of head due to at the entrance of the pipe? So this is a very large pipe, this is a tank here, you can see the tank, and fluid enters a pipe here, enters through a pipe. So this is also another example of sudden contraction. So we have already seen the head loss at this is equal to 0.5 V square by 2G. This is a special case of sudden contraction. So the loss is equal to 0.5 V square by 2G. And what is the loss of head at exit of the pipe here? What is the loss here? So this can also be written as another case of sudden expansion. From here it is suddenly expand to a large area. So this is equal to, for this large area, if you take the velocity will be 0. So this is equal to V minus 0 the whole square by 2G. This can be written as V square by 2G.